As I stated in the other video, we are not only going to talk about direct variation, but also inverse variation. Inverse variation, one's going to go up, the other one's going to go down. And what that's going to look like is we're going to be able to write it in the form y equals k over x. K is still considered our constant of variation. Notice if I rearrange this equation by multiplying both sides by x, I could also state that x times y equals k. So, and again, just verbally it's described that y varies inversely as x. You'll also hear it called or described as y inversely proportional to x. So first thing we're going to do, very similar to the last video, is we're going to first determine if y is inversely proportional to x or not. So I have to determine if I could say there's some k that divided by x equals y each time, or I could just say, could I determine if x times y equals some constant for each of these? So I'm going to ask myself, does 0.2 times 12 equal 0.6 times 4 equal 1.2 times 2? Well, I check and I find out that 0.2 times 12 is 2.4, 0.6 times 4 is 2.4, and 1.2 times 2 is 2.4. Since they all do equal 2.4, they do vary inversely with one another. If I do the same check for part B, again, I'm going to go ahead and say, does 1 times 2 equal 2 times 1 equal 3 times 0.5? Again, just using this relationship here, that if we have two functions that are, if we have a set of values that vary inversely with one another, we should be able to show that multiplying x by y gives me some constant k. 1 times 2 is 2. 2 times 1 is 2. However, 3 times 0.5 is 1.5. So this piece here fails. So this does not vary inversely. We also want to be able to look at modeling inverse variation functions. So suppose we have an x and y that vary inversely. We're told they vary inversely. And we know that x is 3 when y is negative 5. We want to write the function that models the inverse variation. Well, all I need for my function is my k. Notice I can find my k by doing x times y. So I'm going to go ahead and say x times y equals my k, which I can see as negative 15. So I'm going to go ahead and say y equals negative 15 over x. This equation here is going to be the model that represents my given information. Next, third example, there's going to be 4 examples total. We want to look at applying this to a situation. We're also going to use some of the conversion factors to change units. So we're told that heart rate and lifespan of most mammals are inversely related. If we know that a mouse has a heart rate of 634 beats per minute, and we also know the number of minutes in their lifespan, we're going to use this information to find the average lifespan of a cat who has a heart rate of 126 beats per minute. Well, since we vary inversely, I know that y equals k over x, or in other words, y times x equals k. So I'm going to go ahead and find my k, because then I can put it into this equation here, as well as my heart rate of 126. So the dependent variable depends on the independent variable. So it looks like that the lifespan depends on my heart rate. So I'm going to have an x value here of 634 and a y value of 1,576,800 minutes. So I'm going to go ahead and say that my k value is those multiplied together. Once I put that into my calculator, I get a large number. I get 999,691,200. Huge K. So I get y equals that K over my x of 126 beats. And again, I know x is my independent variable, or I know my heartbeats is my x, my independent variable, because lifespan depends on my number of heartbeats. I put that into my calculator and I get 7,934,057 minutes, which is pretty meaningless to me. So for that reason, I'm going to go ahead and I'm going to change that to hours. So because I'm converting units, I'm going to take what I'm given and I want to get to years. So first thing I can do is I can go from minutes to hours. And remember, what I was given was minutes. And I know that there's 60 minutes in 1 hour, but I don't want to end up with hours because from here my minutes will cancel. So I'm going to multiply by another, and this time I'm going to get rid of my hours, and I'm going to go to days because I know there's 24 hours in 1 day. And then I'm going to get rid of my days by going from days to years because I know there's 365 days in 1 year. Now when I multiply straight across, my minutes will cancel, my hours will cancel, and my days will cancel. And I will get 7,934,057 divided by 60 times 24 times 365. And everything but years canceled, so my answer will be years. And I put that into my calculator, and it is approximately 15 years. And if those of you who have any, who've had a cat before, you know, cats usually live between 16 and 20 years. So that is probably a little bit low, but not too bad of an estimate. And most math models aren't going to be exact, but again, that's a pretty good estimate for that. Finally, last thing we want to look at, and also just so you know, I did post a Khan Academy video that goes over how to do this. So if you are unfamiliar or don't remember how to convert between units, please do make sure to go ahead and take a look at that. And then last thing we want to do is look at combined variation, and that's going to be when we have both direct and inverse variations going on. We have some more complicated relationships. So I put some different examples here. For example, if y varies directly with the square of x, here it is varying directly with the square of x. Y varies inversely with the cube of x, so the constant over x cubed. It varies jointly with x and y, so the constant is multiplied by both x and y. Varies jointly with x and y and inversely with w. Varies directly with x and inversely with the product of w and y. So just some different examples. So let's go ahead and do that ourselves. Let's write a function that models z. That model z varies directly with the square of x and inversely with y. So z varies directly with the square of x, so I have to multiply my constant of variation by x squared, and inversely, so I have to divide by y. And I want to write this model, and I want to find z when x is 6 and y is 9. I'm going to go ahead and use the fact that if x is 4, then y is 10, y is 8, and z is 10 to find my k. So I'm going to plug those in and say 10 equals k times 4 squared over 8. Well, that means 10 equals 4 squared is 16, not 8. 16k all over 8. Well, that means 10 equals 2k. So dividing by 2, k is 5. So I know that z equals 5x squared over y, putting in my constant of variation. Lastly, now I want to go ahead and answer this question that I have not done yet. Find z when x is 6 and y is 9. So z equals 5 times 6 squared over 9. So z equals 5 times 36 over 9. Well, 36 and 9 can both be divided by 9, so I can say that z equals 5 times 4, which is 20. I was able to find that from my model. So we've now covered direct and inverse variation, as well as some different combined variations. So from here, you're going to do some practice on that. Please do bring any questions you have in with you to class. And again, if you are unclear of how I was able to do these conversions, please make sure you do watch that Khan Academy video and bring those questions into class as well.